Hey guys, welcome back to Genius Learning. All right, I want to take a look at another E&M problem. And so here we have a cylinder, right? And this is the side view. So what's going on is there's a potential difference between the coaxial conductors. So here and here is the coaxial conductors. And in this region, let's label it here, there is a potential difference. Maybe you can't see that. So let's do, in here, there's a potential difference that goes from here to here. All right, so just the area from A to B. And so we need to find the magnitude of force per unit area on the surface of the inner cylinder. Okay, so let's digest that. We need to find the magnitude of force per unit area on the surface of the inner cylinder. This is the inner cylinder, okay? And if we're looking for a surface, right, then I've outlined this little segment here that's just the surface of the inner cylinder. This is the differential area, a little piece. And we need to find the force per unit area on this little segment and in which direction is it going. So this coaxial conductor out here and this coaxial conductor in here both have a potential difference in between them. And so basically, who's emitting more? Is it going inward towards the inner cylinder, or is it going outward towards the outer surface? And so this inner cylinder, we want to know this little segment of area. We want to know whether it's going, the force per area is going outward or inward. And then it says also the total force per unit length on it. So now if we give this thing a length, some random length, what is the force per unit length? So this little segment is some amount of force. The next segment is some amount of force. The next segment, and so on. So we want to calculate that. What does that mean? Usually I try to write down the units of what they're asking for. So first, they want the magnitude of force per unit area on the surface of the inner cylinder. So they want the force, okay, let's say the force per unit area. So force per unit area, right, per divided by area of the inner cylinder. So force of the inner cylinder. Okay, so I'm gonna go with, this is what they're asking for the first part, and then they're asking if it's in the radial direction or the negative radial. So R is going outward like this, and negative R is going inward like this. Okay. All right, so this is what they're also asking. So let's deal with that first, and then the last question is the total force. So now they want the total force per unit length, right? And our length is calculated by each of these little segments, so we're gonna keep it at F over A. That is our length. Our length is these little surface area squares. Okay, so let's just do it one at a time. So first, force of the inner cylinder per area. All right, let's use good old Gauss's law for, so let's start here. All right, so we're gonna use Gauss's law for electric field. All right, differential area is equal to Q enclosed over epsilon naught. Okay, so using that, let's see. The left side, we're gonna have two intervals, right? We're gonna have 0 to 2 pi and 0 to L. We got electric field, and like I have in the other videos, we're gonna put the Jacobian, and what we're interested in is This is phi. A movement that way is d phi. And so we are length out of r. So this arc length is r d phi. So r d phi. And then we're interested in the height that this thing moves. So where it's at height-wise, which is the length L, and the arc, where am I finding it around the center? And so this is dz. So I have this derived in another video. If you're confused about that, I know I kind of just skimmed over it, but I have a full video on how to derive these. So Q enclosed and over epsilon naught. So if you remember, when we have a 1D situation or a line charge, we have Q is equal to lambda L, right? And when we have a 2D, we have Q is equal to sigma A. 3D, we have Q is equal to rho V for volume. Okay, so these you need to remember. These are how we describe the charges depending on what area or situation we're in. Right now we're in a 1D, right? This is a line charge. We're modeling this inside here, just like, you know, a line charge. So we're gonna write lambda L for Q enclosed, and then epsilon naught on the bottom. So solving, we have electric field 2 pi r. Here we have lambda L. Oh, here we have an L from that integral. Okay, so the r comes out. We don't integrate it. We integrate the d phi, which we get 2 pi, and then we get from the dz we get an L. Here we stay the same, and then electric field, these L's cancel, and we're gonna get lambda over 2 pi r epsilon naught, and that is in the radial direction. Okay, so we're moving outward towards like the outside, away from the center. All right, so this is electric field between the cylinders. That's this area here. Okay, so let me use a little highlighter. So this area here is what we just found. And let's label that. So this is electric field between the cylinders. Okay, so we have that. Now let's find, so we did this. Now let's find potential. Okay, so using phi, changing phi, so this is potential, right? Is equal to the negative integral from B to A, electric field in that region, dotted with differential length vector. Okay, so you can write either phi or you can write V for potential. That's the same thing, right? And here, we're only interested in the region between B and A, because this is the area between the two conductors. So our limits go from B to A, outside in, when it comes to potential. All right, so now let's put everything together. We have the potential is equal to negative B to A, and the electric field in that region is what we calculated here. We have lambda 2 pi r epsilon naught. All right, dr. So this is gonna be simple. We can take out everything, right? And we have 1 over r dr, so that's ln. And we're gonna have negative lambda 2 pi epsilon naught ln of A minus ln of B, but this negative changes and rearranges things, right? So this ln is going to be ln of A over B. So let me just, this here is going to be ln of A over B, right? Properties of ln from these two. And then this negative here is going to make these two flip. So it's going to be B over A. All right, so we have lambda over 2 pi epsilon naught. And then we have ln of B over A. So this is our potential. And we can rewrite this potential, right, using this notation for the 1D, because ultimately we're looking for Q, right? We need Q in order to use electrostatic force equation, which is going to come next. So this is a good representation. This is fine, right? Or we can also write out Q equals, so we can also write out here Q is equal to lambda L, and we could write Q over L is equal to lambda. So writing out what lambda is here, we're gonna get, let's rearrange. So let's see, we're gonna have the potential is equal to Q over 2 pi epsilon naught L, right? Q over L, and then everything stays the same, B over A. So we can write either one of these representations, right? But the one that's gonna help us next is gonna be this one here, all right? And as a matter of fact, from here, we're gonna solve for Q. Okay, so let's do that separate. So we got this, right, that we got, and this is the potential, right? And this is the potential between, sorry, R is between whoa, I can't do anything right now. Okay, so this potential is between A and B. Okay, so R should be greater than A, right? But less than B. There we go. Okay, so the potential that we found is for this region here. Let's make sure we got space. Okay, so now let's go over to this side here and see why we did these two representations, which are both correct, but only one can help us in the following parts. So we wanted this representation here, and now let's solve for Q. Okay, so we're gonna solve for Q. Let's put all this to the other side, and the ln, we flip it, right? Do some algebra, and we're gonna get Q is equal to the potential, 2 pi epsilon naught L over ln of B over A. Okay, so now we have a value for Q, which is our charge. Okay, this is charge. Now we want to evaluate the electric field in the inner cylinder. So our whole purpose of this was to give us a representation of the electric field in this region, right? So this next part might be a little bit tricky, but see if I can clear it up. We're gonna use this, right? We're gonna use electric field. So let's rewrite it here. Electric field is lambda over 2 pi R epsilon naught. It's in the radial direction. Okay, but we're gonna make some changes. We want the electric field of the inner cylinder, right? And so this charge right here can be represented, better yet, this lambda right here can be represented again like we did over here as Q over L, right? lambda, if we solve for, put the L on the other side, is Q over L. So for this lambda here, I'm gonna put Q over L, and the radius that we're interested in goes to A. So only on the inner surface of the inner cylinder. Okay, so we're gonna change two things out of here. We're gonna change the lambda, and we're gonna change it just like we did here. So we're gonna change it to this. And we got that from our 1D charge. And that's gonna be electric field. All right, we're gonna have Q on top, and we're gonna have an L on the bottom, right, from that lambda. Then we're gonna keep the 2 pi, and we're gonna change this R into A, because now this is the radius that we're interested in. So that changes to A, and we still have epsilon naught. Okay, so now we have electric field for the inner cylinder. All right, so this electric field is specifically for this area here, which is what we're interested in. Okay, so we got this, and we need to keep this for what comes right after this. Okay, so it wasn't for this part here, it's actually for the next, right, the part that comes right after. So hold this, right? We're gonna hold that until here. We did this part. Now we're gonna use an equation that we've seen before, and that's electrostatic force. So I'll just write it out. Electrostatic, all right, not moving, force, F is equal to Q times epsilon. Okay, and so we need to actually label this properly, right? Because we have force of the inner of the surface. So let's just write force of the surface, because it's what we want. We want to know outward or inward, this surface here, what's happening to it, is equal to the charge times the electric field of the inner cylinder. Right, so we know what's happening inside this cylinder of radius A, and this side is gonna tell us the force on the surface as a result of the amount of charge and the electric field in the inner cylinder. So this is the representation we want, the labeling. All right, and so now let's plug things in and solve. So this part is gonna be a little bit, let me try to make it as nice as possible. We have F, okay, of the surface, right, is gonna equal Q, and we know that Q can be represented like this. So we got potential, 2 pi epsilon naught L over ln of B over A, right? And then we have electric field in the inner cylinder that we found to be this. So we got Q over 2 pi A L epsilon naught. All right, remember everything is in the radial direction. Okay, so having this, let's do one more thing, and that is change this potential into what we found right here. Okay, so we're kind of jumping back and forth, but really we're just trying to eliminate the variables that we don't need and trying to be left with the things that we do need. Okay, so let's change this potential one more time, right? And that will be equal to this right here. Okay, so let's do that. That's right. Force on the surface. Okay, I'm gonna only write this right now. Okay, so I'm gonna separate this this phi out. I mean the potential. So I'm only gonna write this right now, right? And that's this right here. So I'm gonna write all this. So it's Q ln of b over a over 2 pi epsilon naught L. I write it on top so it's easier when I'm gonna cancel out things. Okay, now this I'm gonna leave just like that, right? I didn't do nothing to that. And so 2 pi epsilon naught L over ln of b over a, that stays the same. Okay, and then our last part stays the same also. Nothing changed here. 2 pi AL epsilon naught. Okay, everything in the radial direction. And so now we're in a much better place to start canceling things out. Okay, so let's do that. So what do we see that can cancel out? We have ln of b over a. Okay, we have an L. Let's see, this L can cancel here, epsilon naught. We got the 2 pi that can cancel. And that's it. Okay, so now let's write everything that's left. We have force on the surface is gonna equal Q squared, right? Q squared, and then on the bottom we have 2 pi epsilon naught AL. So 2 pi AL epsilon naught, and then these two Q's right here are squared. Okay, that's the radial. And one more time, because they want us to prove, or they want us to represent the force in a certain way, we're gonna change the Q back to potential. So this is a good answer. Just like here, we have two answers. This is a good answer if, you know, this is what they were asking you for. Just represent the force as a function of the charge or whatever. But specifically, the problem wants us to make it look like something. And so this is not wrong, but let's change the Q now into this over here and represent it with potential. Okay, so we got force of this surface is equal to Q squared, right? I'm gonna write separate. So let's do that with this. Okay, we're gonna let's do Q squared, which is this here. We have the potential squared. Okay, I'm just gonna do this. I'm gonna write it all and square it. So let's do this, right? 2 pi epsilon naught L over ln of b over a, and all of that is squared, right? Because that's what we have here. And then on the outside, let's just move this bottom piece over. We're gonna have 1 over 2 pi epsilon naught AL, and that's in the radial direction. Okay, so we have this, and let's simplify a little more. We have F on the surface is equal to, let's see, we got 2 L's up here, 1 down here, 2 epsilons, 1, 2 pi, 2 pi, and so one of these gets canceled, this gets canceled, the L gets canceled, and what we're left with is 2 pi from the top. We got an epsilon naught still hanging around. We got an L over A, which is here. And then on the inside, the things that are squared, we got the potential over ln of B over A squared in the radial direction. Okay, so this is the representation they were looking for. Okay, so both are correct, but one is more correct. One is just how they wanted you to represent it. So it's the same thing. They just wanted it to look like this. Okay, so now we have the force on the surface of this inner cylinder. So now we know what's happening in here. And you can see that since it's positive, right? In what direction are we heading? Outward, right? So this right here tells us the direction of the force on this surface. And so since it's positive, we're just going outward like that. I'll draw an arrow. And now let's solve for the total force on the complete surface. And so that's an extension of this length here, the complete surface. Okay, so let me get another piece of paper so I don't write on top of that. 1 second. Sorry about that. Should have known. Okay, all right. So let's do the final part here. Okay, we're probably not gonna need any of this, but if we do, I'll move it. All right, so now the last part, let's do this. So we have our force on the surface, right? We have the electric field of the inner cylinder. We have the charge, the potential, and electric field between the cylinders. So we have here and we have the inner cylinder. So force on the surface, positive, so we know the direction. And now we know this, we know, we don't know the force per area, so we're gonna find it here as the total, okay? And for that, we're gonna need a formula. So this is not part of the first question, right? So for the force of the inner cylinder is just this, and now we want the total force per area, right, of the per unit length. Okay, so here we have, let's see, we're gonna be using, so this is the total force of the complete surface. Okay, and we're gonna be using force total is equal to 1/2 epsilon naught, the surface integral, right, of sigma squared, which is a 2D, you know, surface area, dA, right? So this is the formula that we're gonna use, right? It divides both cylinders with this coefficient, and we're doing the surface integral over sigma squared times the differential area. So let's see what that looks like. First of all, in 2D, we remember that Q is equal to sigma A, right? Now we're gonna need that because since we're doing a small segment on the surface, we're gonna need a 2D representation. Okay, so let's solve for sigma like we did for lambda. We got Q over A, okay? And this is what I mean visually. Okay, we have the cylinder, and right now we're gonna calculate just a segment here. So just a segment on the surface. And so that's why we need sigma now, because no longer are we just doing a line charge, which was in here. Now we're doing surface, and we're gonna do multiple of the surfaces. We're gonna do a bunch of them, so that way it tells us the force per unit length. Our unit length is how long we make this. And so every time we make a measurement right here, 1, 2, 3, this is gonna tell us the force per unit length, per each of these measurements. Okay, so specifically, we're doing that. Now that we solve for sigma, right, let's see what A is equal to. So A is the area of a cylinder, and the area of the cylinder is gonna be the area of this top part, the disk, which is 2 pi, and in this case A, right? It would usually be circumference, 2 pi r. So we want the area of here, of this disk, so 2 pi A, and the length here of how long we're gonna make the measurement for. And so times L. So that's our area. Okay, so we need those two things. And now let's use this formula and get to work. We got F total is equal to 1 over 2 epsilon naught. Okay, we got two integrals, and we got sigma squared, okay, and then r d phi dz, which is the Jacobian for a cylinder. And inside here, we're gonna have q over a, right? So we switched our sigma representation to charge over area. Okay, now let's plug in what we have for q, which is this here, okay, and then what we know for area of a cylinder. All right, so we have F total is going to equal 1 over 2 epsilon naught. This first integral is from 0 to 2 pi. This is from 0 to L. Okay, and let's see. Now we have Q, which is this right here, right? We have potential times 2 pi epsilon naught L over ln of B over A. Okay, boom. And all that is over area, right? Which is 2 pi A L. A because we're only interested in the inner cylinder. And everything here is squared. All right, so let's make sure we got some room. Okay, so we have that. Now let's oh, the Jacobian. Okay, so instead of r, we're gonna write a, because instead of a random radius, we're only interested in a length of a. So a d phi dz. Okay, perfect. So now we are good to go to solve this. So first of all, let's we can simplify it before we solve. Let's this fraction. So what I'm gonna do is this. I'm gonna write out here, right? This fraction that's going on here. We have potential 2 pi epsilon naught L over ln of B over A, right? This is squared, and then this bottom piece is also squared, and we're gonna bring it to the top as 1 over 2 pi A L, which is also squared. So then we can clearly see things that cancel out. All right, so move on to this page. All right, so we have, let's see what cancels out. We have the L's, no L's. We have the 2 pi's, and I think everything else stays. Yeah, okay, so let's evaluate the integral, see what we get. So force total, 1 over 2 epsilon naught, right? I'm evaluating the phi integral first, so I'm gonna get 2 pi from that. The z integral, I'm gonna get L. And then things that I got left over from here, right, are the potential squared, right? Epsilon naught squared still over ln of B over A, and we have an A squared. Yeah, so an A. So everything in here is still squared. All right, and so we need to rearrange it and do a couple of tricks, and we're gonna get to what we need. So we're looking for, so let's be reminded, we're looking for force of the surface per area. All right, this is what we're looking for. So we have the total force, which is good. It's what we need, right? The force of the surface. Now we're getting the total force. Sorry, this is total. So this was the surface, and then this is the total. So an amount of length that the cylinder is. So this is what we're looking for. We have this. Now let's try to get the area underneath. Instead of just multiplying or dividing both sides by A, let's see what we can do with this in here. All right, so I'm gonna write this again, right? And there's an epsilon squared up here, and there's an epsilon down here. And so we can cancel one of them, this one. Oh shit, oh shoot. Okay, so just remember that I canceled one epsilon out. And so let me just write it out here. Where does that epsilon go? Okay, it's squared. Oh, okay. So there's an epsilon squared up there. All right, so let's keep that epsilon there for now. Okay. All right, I'm gonna keep the epsilon there for now. So don't cancel anything. All right. What I'm gonna do first is take out this A. Okay, hold on a second here. So I might have confused myself for this part. Let me start on this part again. I'm sorry about that. See, this is why I don't like skipping steps. I personally get lost. So okay, we're gonna start off here again, and everything here is squared. Okay, so F total, all right, we're gonna have 1 over 2 epsilon naught. All right, we have 2 pi, and we have L, right, from the integral. And oh, okay, that's what I was missing to say. Okay, so now I'm gonna evaluate this inside here. Okay, so I wrote this out right here. That's fine. And then I flip this bottom fraction to the top. And so that's fine. But the L's cancel, right? We have the 2 pi's that cancel, and there's 2 A's on the bottom, and there's this A that's on top. Okay, so this one cancels out, and we're left with one of the A's on the bottom. So I'm gonna write an A on the bottom. Okay, so you see there's 2 A's on the bottom and there's 1 on top. So that's what I was missing before. All right, and then all this simplified to potential over ln of B over A, and we still have the epsilon naught. Where is this epsilon naught coming from? So it's over here. Okay, so I'm just gonna write it here. Epsilon naught squared. Okay, all right, so now we're back. So let's see, we have all of this, okay, and we have this in the inside. Now I have an A down here, okay. What happens if I manipulate this part here to look like A, right? I need a 2 pi A on top. And so let me just, let me work here separate. If I do 2 pi A on top, right? Because that's what I need for this part here to look like A. Then on the bottom, which is this, I would need an A squared, right? So, you know, this part, this, and this are the same thing, okay? And so now let's move forward and write this top part as A. Okay, so the next line is gonna be F total is equal to 1 over 2 epsilon naught, right? I'm gonna write this top part as A. This A squared, I'm just gonna put inside of here, right? And so it's potential, right? We got epsilon naught, we got A, and we got ln of B over A. Everything is squared. Okay, so let's see. I feel like I lost an epsilon somewhere, but you know what? I think that's fine. We need to divide out this A to this side, and finally cancel out one of these epsilons. So we have force total over A that I'm dividing out over here to the bottom, and on the top we're gonna keep this as 1 over 2 epsilon. Okay, and we got the potential over A ln of B over A epsilon now. Okay, and radial direction, right, is equal to 0. And so this is it. This is the force per unit area. Okay, and let's see. So we have, so first let's recap real quick. We have Gauss's law for electric fields. Okay, and then what we did was find the electric field between the cylinders, so that's in this area. Okay, we're interested in what's going on the force of the inner cylinder, so the face of this, and in what direction is the force going, and also the total force per unit length of area. So this electric field is good. Now we're gonna use the electric field and find the potential, all right, between those two cylinders. And we see that we can represent the potential with lambda, right? 2 pi epsilon naught, or we can change this lambda, which is the 1D charge, the line charge, and we can represent it like this. Okay, so both of these are the same. We just replace Q over L with this lambda here. So these potentials are fine. The reason that we did this potential is so that we can solve for Q. And so Q is now the potential 2 pi epsilon naught L over ln B over A. Okay, and so let's see. So now we got the charge. Okay, we're gonna hold that for a second, and we're gonna represent the electric field specifically in the inner cylinder, right? And we're gonna do that using this general notation for the electric field between the cylinders, and we're gonna change up the R, because now we know that we want the inner cylinder, so that R goes to A, and then this Q here is gonna, the lambda is gonna change to Q over L. Okay, so for the 1D. So now we have the electric field of the inner cylinder, so we know what's going on in here. And knowing that, now we can use the electrostatic force. We got F is equal to QE, right? To be more specific, we got the force on the surface of this inner cylinder is going to be equal to the charge, right, times the electric field in the inner cylinder. Okay, so replacing Q with what we have here, we got this, and then we got electric field of the inner cylinder here. Okay, we have these epsilon naughts cancel out, right? The L's cancel out, and we're gonna rewrite the potential in terms of Q. So we're doing a little bit of back and forth because of how the problem wants us to represent the answer. So we're gonna change this, and this is in the green part. We have potential is equal to Q ln of B over A 2 pi epsilon naught L. Then we keep this, right, which is right here. And then we still have electric field of the inner cylinder on this side. Okay, so canceling things out, we see that the epsilons, 2 pi, the L and the ln cancel. And we're left with the force of on the surface is equal to this. And this is correct, this is fine, just like we have two representations for the potential. We're gonna change the Q back to a representation with potential in it. So it's just because the solution wants us to represent it that way, so we're gonna change it back. So this is good, and then now we're gonna change it from this Q to this, which is represented here. So everything is squared, right? Q squared. And we have everything here for Q. And on the side here, we just pulled this out to the side, 2 pi epsilon AL. Okay, so cancel things out. We have two L's on the top, one on the bottom. So one on the top stays, 2 epsilon naughts, one stays, 2 pi, and we have the A that's singled out, and everything in here stays squared. Okay, so this is the force on the inner cylinder, right, on the surface. So by the positive or negative on the radial vector will tell us in what direction it's going. Okay, so since it's positive, we know where it's going. And finally, we're gonna look for the total force of the complete surface. Okay, so that means that we have these segments of dA that we're looking for, and we wanna know the total force per unit length, in this case area, because that's how we're measuring our length. And so we need this equation here. Okay, force total is gonna equal 1 over 2 epsilon naught, right, which accounts for both cylinders, and then the surface integral of sigma squared dA. So in the 2D, we know that Q is equal to sigma A. Rearranging that for sigma, we got Q over A, so charge over area. Okay, we replace this with charge over area, and our Jacobian is R d phi dz. We'll replace R with A because we're only interested in the inner cylinder. And Q, we have all of this, okay, squared, and we have the area down here, which is also squared. Okay, so remember that the area is gonna be this top face and the length of the entire cylinder. So 2 pi A, because that's the radius, and L, because the length of the cylinder. So just doing this algebra right here and this in here, right, we're gonna see this top part stays the same, and then I wanna flip this bottom part, right, up, So that's gonna be 1 over 2 pi AL. We have the L's cancel out. 2 pi cancels out. We're left with epsilon naught squared, and then we have A squared on the bottom. And from the Jacobian, we had an A outside. So this one cancels, and we're left with 1A on the bottom. So that 1A I pulled out, okay? I have 1 over 2 pi epsilon naught. I evaluated both integrals. I got 2 pi, I got L. And then the A that was down here, I pulled it out. Okay, and then what I have left inside the parentheses still is gonna be the potential epsilon naught squared over ln of B over A. Okay, so now here, right here, we do a little magic, and I see that I have 2 pi L, and there's an A on the bottom. Okay, I want this to look like A, right? So I want 2 pi A L, right? All I'm missing is an A on top. That means that I'm just gonna have to add an A on the bottom. So if it cancels out, then it goes back to this. So this representation is the same thing as this, okay? But this helps us because now I have an A on top, and I like A's. So we're gonna keep this 2 epsilon over here. Okay, we have A squared, which I'm gonna move inside to where everything that's squared belongs, right? And so that's it. I'm gonna divide out this A to this side, and now I have force per area, which is what we're looking for, the total force per unit length. And the length was area. Okay, so this is what's left on the right side. Oh, I forgot a squared. So I forgot to square that. And that's it. We have force per area. We have this, right? And that was a lot, but I hope it helped. And thank you guys for watching.